maybe you could start by describing conformal cyclic cosmology model and talk a little bit about the kind of evidence that maybe we should look for, or the evidence that is out there.
Well, the model of conformal cyclic cosmology, which I put forward actually quite a long time ago now, I think it was around about 2005. But the idea basically, there's a long sort of story concerned with where it came from. It really goes back to the singularities. That's the thing I got the Nobel Prize for. That in black holes, you expect to see these singularities. And then Stephen Hawking addressed the question of the Big Bang, which is also a singularity. Places where the curvatures seem to diverge and become infinite, and the theory gives up. So you don't know what to do with the singularities. And I show that you got this situation happening in a black hole. But Stephen Hawking picked up on it and applied these arguments and extended them somewhat so as to apply to cosmology, because you have this Big Bang situation. And the question is, could there have been a previous phase of the universe which sort of collapsed and then through a complicated configuration then expanded out again? But this shows that that doesn't work. So we were stuck with these two kinds of singularities, and the question is what you do with them. And there was a sort of view that you needed quantum gravity to resolve the singularities, which is not an unreasonable view. But it doesn't tell you why they're so different, because the singularities in black holes, one way of putting it, is high entropy. You have a very random kind of singularity, whereas the singularities in the Big Bang, or the singularity in the Big Bang, is very, very regular and smooth in a certain sense, and it doesn't change from point to point. And in fact, the second law of thermodynamics, as we know it, which tells us that the entropy or the randomness in the universe is increasing with time. And so the argument is that, well, we see in the Big Bang, what's non-random about it is the fact that the gravitational degrees of freedom were not activated. It's very random in other respects. You can look at the microwave background, and it's more or less as random as you could expect. The evidence is that it's extremely random. Where does the non-randomness come from? Well, it comes from the Big Bang. And it tells you that there's a certain type of curvature, which is basically the gravitational degrees of freedom, referred to as the Weyl curvature, W-E-Y-L. And the Weyl curvature, for some amazing reason, seems to have been highly suppressed in the Big Bang. And that's not the case in the singularities in black holes. So there's a great puzzle about why they should be so different. For some reason, people never, other than me, seem to worry about this. But it seems to me, if it's quantum gravity, it has to be a very, very strange kind of quantum gravity, which is completely asymmetrical with regard to time. And I had that view for quite a long time. I held that view for a while, and then I wasn't very happy with it. And I mean, it is whatever the theory of quantum gravity is, it has to be a peculiar theory, but it can't be. To be that peculiar seems strange. Anyway, so I thought, well, I just sort of postulated that the singularities in the past, whatever they may be, and the only one we know is the Big Bang, had to be of this kind where the Weyl curvature was suppressed. I didn't know what to do with that until my graduate student, I don't know if he still was at that time, Paul Todd, who postulated a different way of saying it. He said the Big Bang is such that if you imagine it as conformal, and I'd have to explain what conformal means. A good way of understanding conformal is to think of these Escher pictures. It's called circle limits. And what conformal means is that small shapes are preserved, whereas the size is not. So you see in these Escher pictures, there's a very famous one, the angels and devils, circle limit 4, I think that one is. And you see the angels and the devils in the middle. And then as you go closer to the edge, they don't seem to change much in their shapes, but they just get smaller. They get smaller and smaller and smaller until you get to the boundary where they've got to sort of zero size. Now, this describes a certain kind of geometry known as hyperbolic geometry. Don't worry about that particularly. But the point is that it does represent a picture where the conformal geometry, doesn't matter how far you are in the picture, where you are, the structure is the same if you're not interested in how big or small things are. Or if you look, the angles are preserved as the key thing. You look at the angle on the wings of the devil or something, and you see they're the same no matter how close to the edge you get. So this kind of geometry is something which interested me for quite a long time. And it's very useful to think about in connection with things like gravitational radiation, which I spent a lot of time worrying about. And the idea is that you make a boundary, like in the Escher pictures, and you squash it down, and then it becomes just like anywhere else in a sense, except it's got a squashing factor. The only thing is the squashing factor. Apart from that, it's very similar to the rest of the place. And you can do equations out there, and this is the way to study gravitational radiation. So that was a thing that I'd done quite a lot of in the past. So I was quite familiar with that idea. But the sort of complement to that idea is the Big Bang. And the Big Bang, one way of saying how special it is to say you can stretch it out. You see, you're squashing infinity down and making it nice and smooth boundary. And the other is stretching out the Big Bang and making it nice and smooth. And Paul Todd made sort of the idea that what's special about the Big Bang is you can make it smooth. And this gives you a restriction on the Weyl curvature. Not quite strong enough, and I needed a little stronger than that, but his idea was really basically what I was using. So you have this picture of the universe starting from the Big Bang, expanding, and then slowing down a bit, and then doing this exponential expansion, which we see it from observations starting at the turn of the century. And this seems to be what the universe is like. But you can squash down infinity, and it becomes space because of the exponential expansion of what's referred to as the cosmological constant. Because there is a positive cosmological constant, which is what we seem to see, that's a term in Einstein's cosmological constant is a term in Einstein's equations. There's a lot of controversy about it originally, but it does seem to be there. And it seems to be there and it's positive. And that means that infinity, when you squash it down, becomes space-like. That means it's like a time. It's time infinity, but it's a sort of that time all over the whole universe. And that time infinity is a surface which is what we call space-like. And the Big Bang, if you stretch that out using Paul Todd's idea, and it makes it regular, then that again gives you a space-like infinity. And the fact that you can stretch it out is, if you say as your criterion that you can stretch it out and make it smooth, then you get all you need. Second law in the form that the gravitational degrees of freedom are suppressed in the early universe, and it fits in with all sorts of other things. But then the next step for conformal cyclic cosmology, I mean, that what I've said so far, there's nothing outrageous about it. It's not necessarily the way people looked at the problem, but it's you have this initial state, which is time, if you like, time zero, which is the Big Bang, and you need to stretch it out to make it nice and smooth. And then you go to infinity, and there's another time, and you can squash it down to make it nice and smooth. So that was the picture I had. And then I remember thinking about how boring the universe will be in the remote future, where you get these clusters of galaxies, which seem to remain bound as the universe expands. And then they get, the galaxies start colliding, and you get black holes, which start colliding, and you get bigger and bigger black holes. And then there's one dominant black hole, which dominates the whole cluster. And then that black hole starts swallowing material, and it probably swallows most of the entire cluster. Some will escape, but a good deal, proportion, probably most, will get swallowed by the black hole. And then that black hole sits around and sits around and sits around, and I thought, how boring that is. You've got to wait for something like 10 to the 100 years. That means 1 with 100 zeros. Think of that number of years. That number of years it'll take before these black holes start to evaporate away, according to the Hawking evaporation. You see, Stephen Hawking said a black hole has a temperature. The temperature is ridiculously small. In fact, for an enormous black hole, it's ridiculously, ridiculously small, very, very cold. But the universe expands and expands and expands. And as it expands, it gets colder and colder until that black hole becomes the hottest thing around. And then it starts evaporating away. And it evaporates away and evaporates away. And this takes endless time. And finally, it disappears with a pop. And I thought, this is incredibly boring. And then I thought, well, who's going to be bored by this universe? Well, it'll be mostly photons running around, and it's very hard to bore a photon. What I mean by that is not that photons don't have experiences, which I don't think they do, but the time, as far as the photon is concerned, is nothing. That is to say, its creation to where it's going, as far as that photon is concerned, is zero time. So where does it go? Think of the Escher picture again. You see, you've got the infinity, and you can think its photon steps out and goes on to the other side. Well, what's the other side? Normal theory doesn't have another side. So I think, well, what could be more reasonable than the other side should be a Big Bang? You just stick these things together. In order to make sense of this scheme, you have to get rid of mass. Why do you say you have to get rid of mass? Because what is it that gives you the scale of how big things are in the universe? Well, it's mass. Why do I say that? Well, you take the two most famous equations of 20th century physics. One of them is E equals mc squared. Einstein's E equals mc squared. That is that C is just a constant. So it tells you that energy, that's E, is equivalent to mass. So energy and mass are equivalent. That's Einstein's. Even earlier than Einstein, Max Planck had his formula, which was E equals h nu, or hf. E again is the energy, h is a constant, E or f or nu is frequency. So that tells you energy and frequency are equivalent. That's a quantum mechanical thing. Energy and frequency are equivalent. Put the two together, tells you mass and frequency are equivalent. So any massive particle or body or something, massive particle, is a clock. So it ticks away. In fact, for any normal particle, it's a bit higher frequency for most purposes, but nuclear clocks and atomic clocks basically depend upon this fact, that mass is a clock. And if the mass is constant, preserved, it's a very, very good clock. Now, it's the clocks which give you the scale. Distances are defined, you see, clocks determine seconds, if you like. Distances, light seconds. Once you've got the speed of light, the distances are equivalent to the times. So it's the frequencies. So once you have something with a frequency, then it fixes the scale and you don't have conformal symmetry. What happens in the remote future? Well, I just thought mainly photons. It's a little more complicated than that, but mainly photons. They don't have any mass, so they don't have their clocks. What about the Big Bang? Well, there the argument is the opposite, but still even stronger, I think, in a way. It's extremely hot in the Big Bang. What's hot mean? Everything is running around very fast. The particles have an enormous amount of energy, and they have so much energy that the mass is completely irrelevant. They might as well have no mass. So the closer you get to the Big Bang, the more and more irrelevant mass becomes. So the argument is that at both ends of the universe, namely the Big Bang at one end and the remote future at the other, you don't have any way of keeping track of the size. And so this kind of geometry called conformal geometry, where big and small are equivalent, seems to me very appropriate. And in some sense, the Big Bang looks awfully like the remote future. You might say it looks very different. The remote future is very rarefied, very cold. The Big Bang is very hot and very dense. But when you squash down rarefied and cold, it gets hotter and denser. When you stretch out hot and dense, it becomes colder and more rarefied. And they look awfully similar, surprisingly similar. So I've had that view for a while, and I thought, well, maybe that's what happens at the other end of the Big Bang. Other end of the remote future is a Big Bang. And although at first sight or first thought or first something or other, you might think they're extremely different, they're only different in the scale. So once you've lost your scale, they're awfully similar. So this was the birth of conformal cyclic cosmology. The Big Bang becomes a conformal structure. You lose the scale. The remote future again becomes a conformal structure. You lose the scale. And so it can fit nicely onto the next Big Bang. And it explains why the Weyl curvature has to be 0. And you look at the equations and you say, well, it's got to be in the remote future. And so it's got to fix onto a 0 one in the next eon. The next eon, I use the word eon, cosmic eon, from Big Bang to remote future. And I'm saying our universe, I'd rather not use the term universe because the whole thing is the universe, I'd say. But our eon, cosmic eon, began with our Big Bang, ends with our remote future. And then there's another one, and then there's another one. And there was one before us and one before that. So I had this idea for a while. Curiously enough, the first public mention of this was in an interview with Stephen Sackur. I never quite knew how he got hold of this, because I did mention this proposal in that discussion. It's probably somewhere in the BBC archives, I suppose. Be curious to know what I said at that time. But anyway, the idea didn't get picked up particularly by people. But then I began to think that you could have observational implications. And the first thing I thought of was in the process of galaxies, when you have clusters of galaxies, and then you've got a black hole in that, and then there's another cluster, and another galaxy. And a cluster contains quite a lot of galaxies. Our own one is we've only got about 5, I can't remember how many, but there are a lot of bigger ones with thousands of galaxies in them. And this means that every now and again, 2 galaxies within the cluster will run into each other, form a bigger galaxy. Black holes in each will start to feel each other out, eventually spiral around and swallow each other up. And in that process, there will be enormous bursts of gravitational radiation. So these gravitational radiation signals will burst out from galactic clusters whenever the supermassive black holes run into each other. And that signal will be in the form of gravitational waves. Now, that gravitational waves should get through from one eon to the next. That's about the only thing that will get through. I think electromagnetic signals, if they're long enough frequency, ordinary light wouldn't have a chance. But if it's, say, very, very slowly varying, like magnetic fields, that could get through too. But the main thing which can get through would be gravitational wave signals. So what you get is a collision between black holes, this burst of radiation, which comes out, hits the crossover surface, that's where the infinity is and where the next Big Bang starts, goes through and starts to cause some disturbance in the microwave background material. That's the most arguable part of this story, but it should have an effect. And it should have an effect. Well, the fact that I had a colleague who looked for these things. That's an Armenian colleague. This is Vahe Gurzajan. Vahe Gurzajan. I had other people starting to look for these things, and they looked for ways which we had no hope as far as I can see. They didn't see anything. I mean, David Spergel at Princeton, and he got someone to help him to look, and they didn't see anything, which is not surprising because when I looked at the methods, I was very ignorant about what sorts of methods you should use. And later on, I look back, I said, there's no chance they would have seen it the way they were doing it. But Vahe's way was more interesting. And he looked for multiple rings. You see, what you would see, this burst of gravitational radiation will hit the crossover surface. Think of it spreads out. And this is a 3-dimensional surface, so it's a sphere in that 3-dimensional surface. Then you look back, our past cone hits that sphere and it cuts it in a circle. So we should see in the sky circular rings. Pretty hard to see. Later on, a Polish group headed by Krzysztof Meissner and Paweł Nierowski, and they had a third colleague, I've forgotten his name now. And they looked for these signals and found them with a certain degree of confidence. I think it was a 98.4% confidence level, which is not huge, but worth looking at. Vahe didn't analyze it that way. He looked at it in a different way, which was interesting. He looked at it by looking for not single rings, but multiple rings. Because if they are in a cluster of galaxies, collisions between black holes, this will happen several times. So there'll be bang, bang, bang. When I say that, of course, a lot slower than that. But they will come out, and the rings that you would see in the microwave background, they'd be the gravitational signal will disturb the microwave background enough to put a little bit of extra energy into it. And that's what you see. But Vahe's way was looking for multiple rings, so you see at least three. You would only mark it down if you three of them. Consider that it was not significant, less than three. And so he marked down the points where you see at least three of these signals. And it's a very striking picture, because what you seem to see is very non-uniform distribution in the universe. You might say, whatever it is that's producing these signals, it's very strange, because there's this thing called the cosmological principle, which more or less says that the bigger and bigger scale you look for things, the more and more uniform it is. It's just not true, because you see these things, whatever they are. Now, we claim these are some signal from the previous eon. A lot of people, I don't know.
Do you think that there's any prospect for intelligent life from previous eon to send one of these signals?
Well,
because the sky should be teeming with intelligent signals, if possible, if there isn't infinite previous eons.
You see, they have to send signals in the form of gravitational wave signals, because that's pretty well. I don't know, they might use, as I say, very low frequency electromagnetic signals, but the most promising would be in gravitational wave signals. So it's possible. Well, Vahe and I actually wrote a paper on this. Our second paper was on what we referred to as the Fermi paradox. This is the Fermi paradox. It's not really a paradox. I don't know why it's called a paradox, but it's that somehow we don't see enough signals. It's the claim that you would expect to see signals from previous civilizations. But you see, if you're looking in our eon, it might be that they're pretty rare. And the next civilization might be so far off that the civilization has already wiped itself out, or whatever it's likely to do, if our own civilization is anything to go by. It might well wipe itself out. But so you'd be pretty lucky to catch the signal.
So it's possible that the signal has just decayed away into noise.
Well, you see, what we think, I mean, it's not we think, it's only just a suggestion. I rather like the paper because I can use one of his pictures, which shows you this very non-uniform distribution in the sky. And it's non-uniform in two ways. One is it's non-uniform in the sky, so there's just a spread in a certain region, and another region there, and another region there. It's fairly localized. I mean, the size of these regions are, I don't know how many degrees it is, quite significant. But it's also clumped in temperature. You see, the way Vahe looked for these signals was in looking at the variation in temperature. It was a question of low variance he looked for. So the temperature around the ring is there's less uniformity than normal. And that's what he uses. And he uses at least 3 low variance rings. But then you can ask for the temperature. And the temperature, according to the theory, is an indication of the distance. And so what you see is when they're clumped in angular distribution, they're also clumped in temperature. because there's a big one with red spots and another one with blue spots. And this means it's clumped. The coloring is telling you they're clumped in distance. And I find this very impressive. However, I say the Polish people who came along afterwards, we had a lot of trouble with referees, and it was some complicated story, which I won't go into. But eventually their paper, they got lots of rejections. We got lots of rejections too. I think they were right to be rejected, the earlier ones. But the later paper finally got published. And the Polish people, then their paper got published eventually. And this was on these signals first. And that they did an analysis saying it was 98 point. I think they did it both with the WMAP data. You see, there are two different satellites. There was the WMAP satellite, and then there was the Planck satellite. And the WMAP satellite was earlier one. And I think that way they got a 99.6. I can't remember. It was slightly different, but not very.
Okay.
And then the Planck data, and they saw the signals in both. And then I then collaborated with my Polish colleagues, and there were two of them. That was Krzysztof Meissner and Paweł Nierowski, and also a South Korean called Daniel An, who now works in the US, and he did the detailed analysis. Krzysztof had the method of the analysis. And we see a very strong signal for something quite different. These are what we refer to as Hawking points. Now, what's a Hawking point? I'm just calling them that. I think it's a good name. But I've given you the background for this. What happens to a galactic cluster? Well, it gets swallowed by a black hole. And that black hole sits around for something like 10 to the 100 years. And then it evaporates away. And all the energy, pretty well all the energy comes out in gravitational radiation. However, it happens so late that if you think of the Escher picture again, it's as though you're looking right up at near the boundary. Look at those angels and devils right up near the boundary. And it's only at that point does this radiation come out. So it's a point, virtually a single point. And so what we're seeing is that all that energy, which was the entire galactic cluster's worth of energy, bursts through into the next eon. So it would be a hot spot, a little spot, tiny spot of enormously raised temperature. Now, you don't see that because the photons coming from that have to work their way through all these microwave background stuff. They scatter. They just scatter all over the place. And finally, they manage to escape. They can only escape when they reach the surface of last scattering. The surface of last scattering is 380,000 years after the Big Bang. So you have to wait until that spot spreads out to whatever it does in 380,000 years. And that's a little region in the sky, a little spot. So it's a Hawking spot at that point. Okay, we do the analysis. We look for spots of different sizes. And there's one size just shines out like anything above everything else, with a confidence level of 99.98%. We get this paper published in a very respectable journal, the Monthly Notices of the Royal Astronomical Society. Nobody pays any attention. There were some criticisms of it, but not, when you look at all the criticisms, they all referred to the archive paper that we had to take down as one of the conditions of having it published by the journal. None of these papers refers to the actual journal, as far as I can see. I may be mistaken that there is one that refers to it, but all the papers, and strangely enough, even though they criticized our archive paper, which is not so clear as the actual paper makes the point clear, because people get confused and they think we're looking for the same signal and just look in a different place, and they call it what's called a look elsewhere effect. It's nothing to do with that. It's a completely different signal, completely different origin, and we were expecting to see these spots. And they're there. And they're there with this confidence level and published. And actually seen by other people without admitting it. It's quite strange. One of the papers that criticizes us, they say they don't see anything. You look at the paper, and they do. It's in there in the analysis. Very strange.
Maybe following on from this, so people seem to have difficulty accepting the conformal cyclic cosmology.
Yes.
Do you think that this is because it poses such a jarring picture of an infinite past, which is it's almost the opposite of saying that the universe did have a starting point, like a point of initial creation. We're now saying that
You've got to shift your way of thinking. I think that's the thing, and it's hard to do that. See, I mean, I didn't shift my way of thinking for quite a long time, but it was a long time ago. Now, as I say, it was getting on for 20 years, was it? Yes, 2000. Getting on, it's about 18 years ago. I'd have to check up exactly when it was. I can't remember when the Stephen Sackur interview took place. But it was quite curious because he said, when we were going into the studio, he said to me, I usually talk to politicians and people, and I have to say something which I disagree with them. So you have to excuse me. At some point, I'm going to say, I disagree with you, see, or something like this. I'm going to be a bit rude. So I said, don't worry about that, he said to me. So at a certain point, he said, why did you change your mind? So I said, well, I thought that was a good thing in science, to being open-minded enough to change your mind. So it was, but I did change my mind. But the reason to changing my mind was I couldn't see any other way to explain the uniformity of the Big Bang. I think there is a completely wrong way that people kind of relax with. You see, there's a thing called cosmic inflation. And there's supposed to have been, in the very early universe, this exponential expansion, which is not the one we see now, but in the very early stages, in the first 10 to the minus 30 seconds, 30, I don't know, yeah, 10 to the minus 30 seconds or something like that. So the initial blip of the Big Bang, and it was supposed to have done this exponential expansion. And the claim is this smoothed the universe out. It doesn't. It's just wrong. If you reverse time, put the inflaton field in as much as you like, it doesn't get rid of these black hole singularities. I don't know why people take it seriously. But they somehow relax in thinking, oh, well, inflation will smooth the universe out. And that's why it's so smooth. No, it doesn't. No, but they somehow haven't picked up on that point. I find I don't really understand why people haven't picked up on it to the degree they do, except that it is an outrageous theory. I see. It's not in accordance with the standard picture. But nevertheless, a lot of the models that people do put forward are pretty well outside the range of standard cosmological schemes in other ways than this. So it's not clear to me.
I was wondering, so you talked about how black holes have a singularity somewhat similar to the Big Bang, but different
Very
as far as you're
different. Yes,
proposed.
yes.
But there is a picture, maybe in a popular science perspective, of how it would feel to approach a black hole. Would there be any way to describe how it would feel to approach the Big Bang of the next eon?
Well, it's not the same. You see, probably what they're talking about are the horizon. See, black holes, once you're getting close to singularity, you might as well give up because the Weyl curvature just dominates very, very rapidly and was spaghettifies. I think that's the term that Stephen Hawking used to use. You get stretched in one direction and squashed in the other. And that's the sort of thing. It's not something that's pleasant. However, you can talk about what going through the horizon is like, because that's nothing special. It's nothing special in the sense that there's nothing local in the space-time geometry or the physics that would tell you where you are. You just have to know. The navigator would have to say, we've just gone through the horizon. Have you? Oh, I didn't feel a thing. No, you wouldn't. It's just like anywhere else. It's just that you can't signal out from that point. But it's not a local thing. You see, you can't tell locally where the horizon is, because it depends on what might happen in the future. Then a lot more material might come in later, and that means your horizon is further out. And that means you crossed it earlier than you thought. So it's not locally determined. It's determined by some global criteria, and you just trace back and find out what things escaped and what didn't. And those that didn't are out inside the horizon. But there's no local feeling. You'd have to have if you're really determined to go through a black hole horizon, your navigator would have to say, according to my calculations, you should have just gone through the horizon. Didn't feel a thing. You shouldn't feel a thing.
Would you say the same conclusion comes to crossing over into the next eon?
That's a more serious matter because you've got longevity is the problem there. See, you've got to live for as long as these black holes. Well, you see, it's really infinity. But infinity is no big deal in this theory, see, because you could squash it down. And if you become a conformal person, see, it may be that you could have a sort of being which was constructed out of conformally invariant material. I wouldn't recommend it for the kind. You see, we're held together by electromagnetic forces, and then the particles are held together by nuclear forces, and those are the important things here. But just see, when they see if the mass fades out, those things will become less and less important, I guess. You have electrons and positrons, but they might get hydrogen molecules probably. Hydrogen, but that it's not quite clear because you have to know what happens to mass in the very remote future. And the idea is that it actually fades away ultimately.
Is there any region in the current universe, in the observable universe, which is really devoid of mass, which may have any similarity?
No. Well, it might be. Well, you see, there's a lot of dark matter around. The dark matter inhabits pretty well everywhere. It's more dense in galaxies. But this is a material which doesn't have any, there's no confidence in what it's made of. And particle physicists have one or another theory. According to me, the dark matter particles are another form of gravity. And the way to make you have to see how to make the equations work in CCC. And that's a bit of a challenge. But in order to make them work, you need to create something which looks like dark matter. So I think the dark matter is a form of gravity, which is actually massive particles, and they decay into gravitons. So it's a different form of gravity. It's not going to be seen in any of the schemes that particle physicists have, according to my proposal. And this only comes about because when you look at the equations of CCC, you find that you need to introduce a term which looks like a new kind of material. And it dominates the material in the universe. What could it be but dark matter? And as far as we know, when I say we, I don't do any of these experiments, but as far as it's known, dark matter doesn't interact with any other particles except gravitationally. So there is no evidence of nuclear forces, electromagnetic forces, anything else apart from gravitational forces. So to say it's another form of gravity is not so unreasonable. I mean, particle physicists trying to say, oh, well, maybe these are some form of quarks, or no, not quarks, I wouldn't say that. Some form of neutrino. No, there are lots of wild ideas about what dark matter might be, but there's no conventional proposal. And I'm saying, well, that's because it's not conventional. It's a gravitational substance which should decay. And the half-life is something like 10 to the 11 years. So that's longer from the Big Bang till now. So this matter will not decay I mean, a certain amount will have gone by now, but only a small proportion.
In the case that we could send a message, to the next eon,
Yes,
how would you what would you send?
yes. But you see, the thing about sending messages from one eon to the next, which Vahe and I do discuss in this paper on the Fermi paradox, we talk about it, discuss it in any length. No, not really. And I'm not quite sure whether we even think about what kind of signal. I think the best signal for these people you see, that would be gravitational waves. So it would be gravitational wave signals, but it's only one way. They could signal to us. We can't get back to them. However, you could imagine that, you see, unlike with the Fermi searches for other galaxies, you are now looking for civilizations which are really advanced. And these are the ones that manage to struggle through some dark period like what we're having at the moment, which doesn't look very fruitful to me. Okay, we might survive, but we might not. Maybe they've found a way to settle down and avoid conflicts and not use nuclear weapons on themselves and things like that. So, and they maybe send us a signal and say, look, here's some good advice for you. So possibly these very advanced, you say, well, you're looking at those civilizations which really lasted for a long time. And certainly would have to be much longer than we've gone on for so far. And they would have to develop their technology to a degree where they could send gravitational wave signals of substantial character, which we can't do. But maybe you could imagine manipulating planets or something in some complicated way, and I don't know what. I have no idea. But then we're not in that stage of the universe to have any idea. There may be a way of sending signals of a different kind, and maybe sending information which is useful to human civilization.
But maybe as the founder of the theory, you really would be able to write a message to people in the future.
Oh yes, yes, that would be right. Yes, either to our
Your voice has gravity in this situation.
Yes, that's true. Yes. Well, unfortunately, we're not close to being able to do that. I mean, we can't send substantial gravitational wave signals. They're pretty weak, the ones we could send. I mean, you could have massive bodies going around, and you could try and influence the moon's motion or something. I'm not quite sure what you'd do. You really need a lot of mass to manipulate it in ways which would contain a signal. It's very hard to see how that could be done. But yeah, in principle, sure. That's maybe what we ought to do. But I don't think we've got any good advice to tell anybody just yet. Maybe when we settle down a bit, there might be some good advice we can transfer to some of the similar. Or maybe you see we can pick up on what other civilizations have sent out. That's the more promising thing, I would have thought.
Propagate the signal.
From them.
Maybe, yeah.
Yes. No, that would be a better chance. But still, you don't know what kind of signal. Probably gravitational waves. The ones we were looking for, you see, although they are gravitational signals getting through, so we claim, what you're actually seeing are electromagnetic signals. So how that gravitational energy transfers itself you lose a lot that way, of course. So maybe if you could directly pick up the gravitational waves, that would be much more strong. It would be a much stronger signal. It's just that we don't have appropriate detectors, I suppose. I don't know. It's an interesting question. Maybe they're there. There could be signals already there in the LIGO data, if you knew what to look for.
It's kind of an incredible proposal. I like that.
Yeah,
That's good.
I just have to think about that because you'd have to look for. I mean, these might not be signals. I'm not thinking now of deliberate signals. I'm thinking more of black hole encounters. So those black hole encounters that we do seem to see should be accompanied by gravitational wave signals. So we'd know where to look for them too, because they're in these rings. Nobody's looked, I'm sure. Worth looking. Whether LIGO is set up to look for that, I don't know. Worth thinking about. I mean, there are other ways people look for gravitational wave signals, which is in neutron stars, which I was just hearing about on a Zoom meeting. And apparently they can pick up gravitational wave background signals. It's just because the neutron star, these are pulsars. The timing is so precise that any disturbance in the timing can be picked up, and you can see different pulsars. And if there's something which look at disturbance, like a disturbance in the timing of the pulsars, this could be attributed to gravitational waves. It's worth looking at all these things. I mean, there are also detectors of other kinds which one could. I have a colleague, Yvette Fuentes, who's at Southampton, and she's setting up experiments using Bose-Einstein condensates. And one of the things that she was interested in previously is using Bose-Einstein condensates to build a gravitational wave detector. So if she could do that, that would be. They're much more tunable. You see, the LIGO is all sort of locked into what you've got there. You can't change it. Whereas I suppose the pulsar ones might be more promising, but the Bose-Einstein condensate ones, they don't exist yet. They'd have to be built. Yeah.
Okay, that's incredible.
But you're right. There are possibilities for looking at gravitational wave signals, which would be very relevant to CCC.
Oh, that's great. Yeah, I do have a friend that worked in quantum computing, and they built this device where they magnetically trap these Bose-Einstein condensates. And he said it's incredibly sensitive to gravity, as in it's enough to distort the drop. So you essentially have a drop of the condensate, and the gravitational field of the Earth will distort the drop, and they have to correct the magnetic field around it. So I can see this line of thought.
Yeah, that might be a way to do it. Yeah, that's interesting.
Thanks so much for your time. I mean, this was really like an honor.
It's a pleasure for me.
Incredible.
No, and if other people can get interested in these issues, I'd be only too pleased. Seems to me there are quite a lot. There are other things that one could look at. I'd have to think of them on the spot. Certainly, gravitational wave signals is one directly, because they've only been indirectly looked at so far. You see, there's another feature of all this, is the non-uniformity, because we do notice that the signals coming from are not uniform over the sky, which seems to suggest that the universe is, on a big scale, is not as uniform as people tend to think. Now, in the quasar observations, these are looking at signals from galaxies, but they are to do with gravitational collapse too, I guess. The beam of light which comes out of a spinning supermassive black hole in the galactic center of the galaxy. So that's what people think these things are. Yes, the beams that show up. And these are the sources of the quasars. But apparently the distribution of quasars is very non-uniform. And there are some very big ones, sources. And one of these big ones is fairly close to one of our. You see, I should explain a little bit more of the signals that Vahe seems to see. There's a red one and a blue one and a green one. Now, the red one, for two complicated opposite reasons, is the distance one. And the blue one is the closer one. Now, the closer one means that is within our particle horizon. You see, when we look back in convention cosmology, there's a thing called the particle horizon, which means we can't see any of the universe outside where our past light cone hits the Big Bang. And then outside that, we don't get any information from. Now, you do get these signals, because if you have colliding black holes in the previous eon, they can be outside our particle horizon. Now, the red region, according to the theory, is outside our particle horizon. The blue region is inside our particle horizon. Now, the blue region, whatever happens as it crosses over into the next eon, might easily produce a larger distribution of matter and maybe a larger distribution of black holes and therefore more quasars. So it might well be that the distribution of quasars is related to the signals that Vahe sees. I'm talking about his because the Polish analysis wasn't in the case, you couldn't tell the distance by this way, just to detail the analysis. With Vahe-Gerzejan's way, you could tell. And so you can tell that the blue region is within our particle horizon. So whatever it went through, and maybe a lot more Hawking points then, I mean, you wouldn't see them because you can only see the Hawking points on our past light cone. But there are lots more which you don't see inside our particle horizon. Now, those ones inside could create more galaxies and therefore more signals of the other kind, black hole collision signals. And so the fact that we see a big red region could correspond to the quasar distribution.
Thanks so much for your time. It's been a real honor and a pleasure to hear your ideas.
It's been my pleasure. I always like to explain these things. I like to have an excuse.